All right, today's lecture we're going to discuss covalent bonding for this is part 3, and part 3 is going to deal with specifically molecular shapes. One of the things we've kind of figured out how to bond covalent bonds and single, double, triple bonds, and how to demonstrate that using Lewis dot structure or a structural formula. But one thing that we haven't gone over is molecular shapes, and today that's kind of what we're going to deal with. And when you draw them, sometimes you're drawing them on a two-dimensional surface, and as a result you get a two-dimensional shape, and that's not really what they are. So we want to make sure that we understand what the actual shape is in a three-dimensional world. And part of what this deals with is something that's referred to as the VSEPR theory, which is the valence shell electron pair repulsion theory. It's a big fancy name. I'm not going to worry a whole lot about it. But basically, if you really want to sum it up, it's basically the idea that electrons repel each other. And particularly, we're going to focus around the central atom. Is because electrons repel each other, they're going to push each other away the maximum distance possible in a three-dimensional shape. And so as a result, depending on how many electrons you have around a central atom, it will push itself into a unique shape. So to help us with this, there's a chart in your books on page 171 that's going to help us. So if you want to follow along in your books as well as we go through this. So we're going to start with this compound right here, just as an example, and there's a lot of different examples we could do. We're going to start with this, and the other day we learned that, okay, how do I figure out how to draw this? And that's kind of the first step, is drawing this and figuring out, and from that point we'll figure out what the shape is. And we have two elements here. We have hydrogen and phosphorus, and the way we've said that we figure out how to draw this, we need to figure out first what our central atom is. And our central atom is always the one that can form the most bonds. So I'm going to take a look at hydrogen. Hydrogen has one valence electron. It needs one valence electron, so it can form a maximum of one bond. Phosphorus has 5 valence electrons, and it needs 3, so therefore it can form a possible 3 bonds. So if I take a look at this, then I'm going to find out that phosphorus is the one that ends up winning out. Phosphorus is the one that can form the most bonds, and so therefore it's going to be my central atom. So if I move on, and I'm going to actually draw this here using structural formula, here's my phosphorus atom, and it has 2 valence electrons to start with, and then it would have 3 other ones here. We're not actually going to write those in, so we're going to take those away because we're going to bond those. We're going to form a single bond with my 3 hydrogens here. And we're just going to use the structural formula, the little dash there showing that there's a single bond between hydrogen and phosphorus. And if you remember, each of those dashes represents a pair of electrons. And for our purposes, when figuring out the shape or the geometry of an atom, what I'm focused in on is the electrons around the central atom. So I really don't care about the electrons on the outside. If this was, let's say, chlorine instead of hydrogen, I had 3 chlorines bonded to phosphorus, all with a single bond, and the chlorines had other electrons around them. I'm not worried about those. I'm only worried really about the electrons around the central atom. And so I'm worried about this one, these electrons here, and these electrons up top. That's what I'm really worried about, are these guys here, is what I'm worried about. So all of those electrons are really what I'm worried about and what I'm going to count. And there's 2 things that I'm going to take a look at when I'm figuring out the shape. And there's kind of 2 guidelines that you need to follow. Rule number 1 that I'm going to examine is I'm going to take a look at the number of electron regions. Okay, so that's the first thing that I want to take a look at, is the number of electron regions. So that's kind of the first thing I look at. And if you're looking at me and like, well, what's an electron region? I don't understand that, Mr. Rogers. That's fine. Let's go back here. Electron regions are anywhere around the central atom where there is an electron. So if we back up here, let's take a look. Anywhere around the central atom, first of all, where's my central atom? This guy right here is my central atom. So once I identify him as my central atom, do I have electrons? And remember, there's only 4 possible orbitals here to find the s orbital, and then the 3 orbitals for the p that are sides that are representing those. So if we want to look at each of those orbitals as top, bottom, left, right, we can do that. Do I actually have electrons there? Well, these 2 right here are electrons, and so that's an electron region, so that's 1. There's electrons here in this bond, and so that's 2. There's electrons here in this bond, so that's 3. And then there's electrons here in this bond, so there's 4. So that's how I would look at that, and so we'll take those again. So when I come back to this question, how many electron regions do I have? My answer to that would be, well, I have 4 electron regions. It's as simple as that. It's real easy, and you can't have more than 4. You can have less than 4, but you can't have more than 4 electron regions around your central atom. The next thing, or next basic rule that I want to find or look at is similar with one slight difference. It's my number of bonds. Okay. How many bonds, or number of bonded regions sometimes is the way we refer to it as well. So let's go back to this slide right here, and we take a look at our atom again, and we had 4 regions, and I want to check and see if all of those regions are bonded. So I'm going to take a look here. Well, here was one of my electron regions, but is it bonded? Well, the answer to that would be no, so it doesn't count. Even though I have electrons there, it's not a bond. Now this one has electrons, and it is a bond between hydrogen and phosphorus, so that would be one region, one bond. This would be my second bond, and this would be my third. So even though I have 4 electron regions, not all of them are bonded, so only 3 of them count for kind of my second question. So when I come back over here, how many bonds do I have? My answer to that is 3. And so when I kind of put these 2 together, and this is where the chart comes in, if you want to, you can memorize it, but you don't necessarily need to. I can take a look, and the first thing I look at is there's 4 regions, and there's 3 bonds, and when I match those 2 up, I come up with the shape, and in this case the shape is what we call pyramidal. And if you look in your books, they have a nice little illustration of what a pyramidal shape is. I'm not going to attempt to draw that because you guys have seen my drawing in class, and it's unique, let's put it that way. And so that's how I would figure out what the shape is this would be a pyramidal shape. And this is also going to play a little bit of a role a little bit later. In our next discussion, we're going to talk a little bit about what is a polar molecule, and the shapes of substances can determine what a polar molecule is. So let's go ahead and do another atom there. Let's take a look at something like, here we go. Let's go. Let's say I have a situation where I have sulfur and it's bonded to fluorine. So again, I'm going to try to figure out what's my central atom. Sulfur has 6, it can form 2 bonds. Fluorine has 7, it can only form 1 bond. So sulfur is going to be my central atom. So if I go to draw this whole thing here, I have sulfur in the middle, and it has 6 valence electrons here, and then I'm going to go ahead and draw fluorine, and so here's fluorine. Fluorine has 7 valence electrons, and then here's my fluorine, and then I have another fluorine as well, so we're going to draw it down here. And there we go. We've got our fluorines and our sulfur. They're bonded together. If you notice, the octets for all of them are complete. So that we could draw it that way, or we could draw it using the structural formula. I'm going to go ahead and draw it using the structural formula here in just a second. So let's redraw this. Let's put sulfur, and we're going to form a single bond with fluorine and a single bond with fluorine down here. And then I do need to, around the central atom, go ahead and draw any other valence electrons that are not bonded. I'm not going to worry about around the fluorines. And so here I have my molecule, and I want to determine its shape. What shape is this? And so the first thing, if you remember, we go on back here, number of electron regions is, I need to look around my atom, how many electron regions do I have? And I'm going to go back to my formula here. Well, around my central atom is sulfur. That's what everything else is bonded to. And so I'm going to take a look at that. And in this case, I have electrons right here, and I have electrons right here, and electrons right here, and electrons right here. And so I have 4 regions. Remember, we can't have more than 4 regions around a particular central atom. So I have 4 regions of valence electrons. So if I was to come back over here, I would say I have 4 regions of electrons. If you remember, the next thing we want to look at is how many of those regions are bonds or bonded. And so that's our next question. I had 4 regions, so I can have a maximum of 4 regions that are bonded. Do I actually have that? So I'm going to look here. I'm going to take these away here, and I have 4 regions, and as I look at this first region here, point here, that's not a bond. And that's just a pair of electrons that are not bonded to anything. Same thing here. This is a pair of electrons that's not bonded to anything, so neither of those count. This region right here does happen to be bonded, and so it does count. Same thing with this one. This region does count as well. So both of those regions are bonded, and so as I come back to my question here, number of bonds, I have 2 regions that are bonded. So as I look, I have 4 total regions, 2 of which are bonded, and if I look on my chart and kind of match those up, 4 and 2 together, that would be a bent shape, and it would be bent 109.5. I need to be specific on that situation in terms of what bent, because if you'll notice on the chart, there's 2 different bent shapes. There's a bent 120 and a bent 109.5, and that depends on how many different regions of electrons you might have. So that's more or less how you use the chart, is you're always going to start with counting the number of regions around your central atom, and then you're going to take a look how many of those regions are bonded, and then once you figure those 2 things out, then you go and look on your chart and view your shape. And that's basically how you determine a molecular shape.